All right. Okay, so I'm going to talk about variants of phylogenetic diversity on phylogenetic networks and how we can optimize them, or what's the computational complexity of optimizing them. And this is joint work with Magnus Bordovich and Charles Semple that we did earlier this year, all virtually, so our meeting on Zoom, because I got asked about that in a previous talk. Okay, but why do we even care about phylogenetic diversity? Well, phylogenetic diversity is a measure of biodiversity, and investigating how to optimize that is mainly motivated by the fact that the world is currently facing the 6th major extinction event with hundreds or thousands of species at high risk of extinction. At the same time, financial means in biodiversity conservation are often limited. And so what happens is that policymakers or conservation biologists are often forced to prioritize species for conservation. And often the aim is to conserve as much biodiversity as possible, because diversity is often seen as potential for future development or for future things to happen. However, if we want to conserve as much diversity as possible, we need some way of measuring it or quantifying it. And so there are several ways of how we can try to measure biodiversity or quantify it, and one is called phylogenetic diversity. And so this concept of phylogenetic diversity was introduced in 1992 by Daniel Faith, an Australian conservation biologist, for phylogenetic trees. And so this paper from 1992 has been very influential. So the last time I checked, it was cited almost 3,000 times. And so the concept of phylogenetic diversity on trees is fairly simple. So assuming that we are given a rooted phylogenetic tree on some leaf set X, so in this case, the leaves are X1 up to X6, and where the edges are assigned non-negative weights, representing either time or genetic distance between species. And given such a tree, the phylogenetic diversity score of a subset S of the species is simply defined as the sum of branch length in the subtree of T that connects the leaves in S and the root of T. So in this example, if we're going to calculate a diversity score of X2, X4, X6, then we would need to consider this red subtree here induced by the leaves X2, X4, and X6 and connecting it to the root. And so in this case, we would get a value of 15. And so Daniel Faith mainly, or the motivation for this measure that Faith had was he wanted to use phylogenetic diversity, or this measure, as an approximation or a proxy for feature diversity. And there are several assumptions under which this is sensible. The first assumption is that given those edge length here, we assume that features, whatever features might be, you can think of them as certain traits, for instance, certain pharmaceutical properties of plants or any other conservation features or traits of interest. So the first assumption is that they arise proportional to edge length. So on a longer edge, we would expect more features to arise than on a shorter edge. And then the second assumption is that a feature arises only on one edge, and once it has arisen, it is never lost. So in particular, all species that descend from a particular branch in the tree are assumed to have all the features that arose on this particular edge. And in this setting, the phylogenetic diversity score is then proportional to the set of features that are present in the set of species. And so whether this is always the best model, or whether we always want to maximize or optimize this measure of diversity is another question. There's debate on this. But as I said, this paper has been quite influential, and phylogenetic diversity is used a lot. And so now in the conservation setting, where there are limited resources or limited financial means, one central problem is the following. Suppose we have this tree, or we have a tree on leaf set X, and we want to conserve as much diversity as possible, but we cannot conserve all, let's say, N species. But suppose we can also only conserve K species. And this leads to the following optimization problem. Given a phylogenetic tree T on taxon set X and a positive integer K, the aim is to find the best subset of K species that maximize the value of PD. Or in this problem, I'm phrasing it, we are trying to determine the maximum value of PD of S over all subsets of X with cardinality K. And on trees, this is easy to do. Basically, a greedy algorithm works. So what we do is we start with one leaf that is furthest away from the root, and then sequentially we add more leaves, and in each step maximizing the incremental increase in PD. And this was independently shown by Paddy and Goldman and Steele. Okay, so but this is the story on trees, and the problem gets more complicated if you make it more realistic by, for example, incorporating conservation costs, budget, or extinction probabilities, for instance. But for now, we're just trying to think about this simple problem. But of course, my talk is not about phylogenetic trees. We were thinking about this problem on phylogenetic networks. And so it turns out that the evolution of some species or some groups of species or organisms is not always best represented by a phylogenetic tree, in particular if there are processes of reticulate evolution, such as hybridization, where two distinct species form a new species, or horizontal gene transfer, where genetic material is transmitted from one species to the other. And if this is the case, we get a phylogenetic network. And I'm going to formally define that in a minute, where we get this more complex structure that is not a tree. And so the question is, how can we define phylogenetic diversity for phylogenetic networks? And then what is the computational complexity of determining the maximum PD score for these variants on different types of phylogenetic networks? And so there had been some work on PD for unrooted networks, in particular split networks. And Marike and I have a paper on that as well, where we mainly introduced different approaches to defining PD on networks. But in this project with Charles and Magnus, we have defined additional variants, and we looked into the optimization part of it. Okay, so just to have everyone on the same page in this talk, I'm going to talk about rooted binary phylogenetic networks, which are rooted acyclic directed graphs, where we have a root vertex on top here that has in degree 0 and out degree 2. Then all the vertices of in degree 1 and out degree 0, we call them the leaves, and they are identified with X, so with our set of species. And all other vertices have out degree 1 and in degree 2, like this one or this one. These are the reticulations, or they have in degree 1 and out degree 2, like this one, and we call them tree vertices. So those kinds of networks is what I'm going to talk about. And additionally, we assume that we have edge weights on all the edges of this network, again representing, for instance, genetic distance between species. Okay, and two particular classes of phylogenetic networks that will play a role in the following, or that I'm going to mention, are normal networks and level 1 networks. Okay, so first of all, what is a normal network? Well, this network N here is normal. So in a normal network, we have different restrictions. So first, we cannot have stacked reticulations, which means we cannot have two reticulations where one is a parent of the other. We also cannot have sibling reticulations. So we cannot have a pair of reticulations with a common parent. And this is then, those two conditions, they also define a very well-known class of tree-child networks. But then in addition, in a normal network, we also cannot have shortcuts. Where a shortcut UV, like this one, is an edge between two vertices U and V that are also connected by a path. So if you look at this, we have this arc UV, but we can also go this way and reach V from U. And so if you don't have that, it's a normal network. So N is normal, N prime is not normal. And normal networks are, so we have those restrictions, and they are a kind of simple, or at least restricted class of networks that behave nicely in many ways. And so that's why I'm introducing them here. The other type of network that is often considered to be simple is a level 1 network, where a level 1 network is a network such that if you look at the cycles in the network and think of them as undirected, they don't share any vertices. So N prime, there's only one cycle. So this is level 1. But if you look at N, then there are two induced cycles, this one, and they are not vertex disjoint. And so this network is not level 1. But anyway, the message here is normal, and level 1 networks are both defined by certain restrictions. They're both considered simple. And I'm we're going to look at the PD problems in particular for those two types of networks. Okay, but back to the original question, how can we define PD for phylogenetic networks? So in the following, I'm going to introduce 4 variants of PD on networks, discuss how they are related to each other, and then talk about this optimization problem. So the first measure that we introduce, or that we reintroduce, is Charles Magnus and I call that all-path PD. In the paper with Wicke, it was originally called subnet diversity, but we changed it to all-path PD as this is maybe a little bit more descriptive of what it is. So given a phylogenetic network N on some leaf set X, considering a subset S, we define all-path PD of S as the sum over all edge weights over all edges that are ancestral to at least one taxon in S. Or in other words, we consider the induced subnetwork on the leaf set S that connects those leaves with the root. So in this example, for all path PD of X2, X4, X6, we get this red induced subnetwork. Adding up the branch length gives a value of 22. And so all path PD is maybe the most natural generalization of diversity PD on trees, because what we kind of assume here again is that features arise proportional to edge length, and the species inherits all the features from any of its ancestral edges. So that's the first measure we can think of. And now, thinking about all path PD, we can define or think about an analogous optimization problem to the one I mentioned for trees. So given a network N on taxon set X and a positive integer K, the objective or aim is now to determine the maximum value of all path PD over all subsets of the leaf set of cardinality K. This is our optimization problem. And it turns out that this problem is NP hard. And it cannot be approximated in polynomial time with approximation ratio better than 1 minus 1 over E unless P is NP. And the way we prove that, I'm just going to give you the idea, I'm going to show you the gadget, is reduced from maximum coverage. So this maximum coverage is a well-known NP-hard problem that goes as follows. We are given a collection S of sets. So S in this case is a set of sets and some positive integer K. And now the aim is we're trying to find a subset S prime of S containing K elements. So we're trying to find K sets such that the number of covered elements is maximized. This is the maximum coverage problem. And now, in order to show that our problem is NP-hard, we basically take an instance of this problem, translate it into a phylogenetic network, and show that if we could solve our problem in polynomial time, this problem could have also been solved in polynomial time. And so here's just how the gadget looks like. Suppose this is taking an instance consisting of 4 sets, S1, S2, S3, and S4, that together contain the elements E1 up to E9. So the particular sets are given here. And so what we do is we take any phylogenetic tree on leaf set E1 up to E9 in this case. Any tree would work, we're just using the caterpillar. And we then assign all dependent edges length 1 and all other edges length 0. So that's the kind of upper part. And then we turn it into a phylogenetic network by introducing reticulations. And we introduce them in such a way that now if you think, for instance, of S1, that all the elements I can reach from S1 are exactly the ones that were part of S1. Like if I go from S1 up here, I can get to E1, I can get to E3, and I can get to E4. And so we do that for all the sets, and we just need to make sure that this construction is a phylogenetic network and it's binary. So we refine vertices, but in the end, we get a network that looks like this. And now if you consider any subset of the leaves, so let's, for instance, look at S1 and S2, then by the way we chose those edge lengths, it turns out that the all-path PD score of S prime is exactly the cardinality of the elements that we cover in this union S, in S prime S. For instance, S1 and S2, we would cover E1, E3, E4, E2, E5, E6. So we would cover 6 elements. And if you calculate the all-path PD score for S1 and S2, the way we constructed this, we just end up getting a value of 6 as well, because we're covering 6 edges with weight 1. So those two problems have the same solution. And from that, we can deduce that our problem is NP-hard. Okay, so this is just the rough idea. And as for maximum coverage, it is known that there's no polynomial time approximation algorithm yielding an approximation ratio better than 1 minus 1 over E, unless P is equal to NP. And so the same holds for our problem. However, and I didn't include that on the slides, but the way or an approximation algorithm that gives this ratio is a greedy algorithm. That's analogous to the one we had on trees. So we start with choosing one leaf that is furthest away from the root, and then sequentially adding more leaves, always maximizing the incremental increase in PD. And the reason why this works is that we could show that all path PD is a submodular set function, and it's non-decreasing, and then by standard. But those particular maximization problems for submodular non-decreasing set functions are well studied, and it is known that greedy yields an approximation ratio of 1 minus 1 over E. Okay, so we at least have this approximation. But in general, this problem is NP-hard. And so you might wonder, is it maybe easier to do if you restrict the network type? So the first thing we looked at is normal networks, and it turns out that this problem stays NP-hard even when the inputted phylogenetic network is restricted to be from the class of normal networks. And if I just go back one slide, so this network, if you look at it, it's not normal, because for instance, we have a reticulation here that's the parent of another reticulation. But what we can do is we can make it normal by attaching additional leaves, attaching them on zero-length edges. So kindly slightly tweaking the construction, we could show that we can still reduce from maximum coverage. And so the problem is still hard, even if the network is normal. Okay, so that's the bad news. It's hard when it's normal. However, there's also some good news for all path PD, and that's the following. So we could show that if we consider this other class of simple networks, namely level 1, then the problem can be solved in time polynomial in the number of leaves. And essentially the idea here is that we can find for level 1 networks, there is a certain way to decompose the network into 2 trees. Not necessarily phylogenetic in the strict sense, because you might have degree 2 vertices, but we decompose it into 2 trees, such that those 2 trees cover all the edges of N, and such that the all-path PD score of any subset of the leaves is the sum of the 2 PD scores on the trees. And so this implies that our problem of optimizing all-path PD on the network reduces to optimizing phylogenetic diversity across 2 trees. And this is, again, a problem that had been studied before by Magnus, Charles, and Andreas Birner, who showed that this can be done in polynomial time for 2 trees. For 3 trees or more, it's also NP-hard. Okay, but at least for our all-path PD measure, we have one positive result for level 1. Okay, however, as I mentioned earlier, all-path PD is probably the most general extension of PD on trees to networks, but you might also say that it is a little bit unrealistic in the sense that we assume that all features are inherited along the edges. And so in particular, if you think about a reticulation like this vertex V1 here, what we assume is that V1 inherits all the features from, let's say, parent 1, and it also inherits all the features from parent 2. And so this is maybe a little unrealistic. It might be more realistic to assume that a reticulation vertex inherits some proportion of the features from parent 1 and some proportion from parent 2. And we try to model that or incorporate that by introducing a second measure, and this is what we call network PD. So for network PD, first of all, for each reticulation arc in the network, so for each arc that is directed into a reticulation vertex, we assume that we are given some inheritance proportion or inheritance function P of E, or inheritance probability that gives the proportion of features of the parent vertex U that are present in the child V. And assuming that we're given this information, we can then consider for each subset of the leaves S and each arc in the network, now any arc, either reticulation or tree arc, we consider gamma of S and E to be the probability that a feature arising on E is inherited by some taxon in S. And based on those two assumptions, we now define network PD, which will now depend on the network N and this proportion function P as the sum over all edge lengths in the network, where each edge is weighted by the probability that the features arising on it are conserved or preserved by at least one taxon in S. So this is network PD. However, if you think about this carefully, and you notice that one thing that we might do or that we can do is we can set P to be 1 for all reticulation edges. And then what we get is we get all path PD. We get what we assumed before, namely that a reticulation vertex just inherits everything from its parents. So setting P equal to 1 for all reticulation edges in the setting of network PD reduces network PD to all path PD. And so thus the following corollary is maybe not too surprising. That says that now trying to find the maximum value of network PD, so considering this max network PD problem, this is also NP hard, even when the inputted phylogenetic network is restricted to be a normal network. And this just follows from the fact that we can reduce to all path PD. And again, it cannot be approximated in polynomial time with approximation ratio better than 1 minus 1 over E unless P is NP. Or what we, just as an open problem, what we currently don't know is whether this result we have for all path PD in terms of level 1, whether we can say anything about network PD for level 1. We haven't really looked into that. Okay, so that's the second measure that's maybe a little bit more realistic. However, with the way I set P to 1 for all the edges, you can argue that this is not realistic. In particular, we might want, fixing a reticulation vertex, we might want the proportion of features it inherits from one parent and the other to sum to 1. We probably don't want them, or don't assume that a hybrid species doubles its set of features, for instance. And so if we do that, if we introduce the restriction that inheritance proportions for each reticulation with incoming arcs E1 and E2 add to 1, so we have P of E1 and P of E2 is 1, then we could show that we can get lower and upper bounds for network PD by considering the following two measures of PD: max weight tree PD and min weight tree PD. And so for those two measures, what we do is we consider with our phylogenetic network N, we take some subset of the leaves S, and now we look at all the trees and induced trees in the network. We call them connecting subtrees that connect the leaves in S and the root. And for max weight tree PD, we try to find one such tree of maximum weight, or the value is the max weight tree PD is the value of a maximum weight connecting subtree. And for min weight tree, we try to find one of minimum weight. So here's an example for this network I showed before. And for max weight tree PD, in this case, we get a value of 19. And this is given by this red connecting subtree. For min weight tree PD, we get a value of 16. And this is, for instance, realized by the blue tree given here. But in case of min weight tree PD, there's another tree that gives this value, because instead of using this edge, I could also have used this edge. Okay, and max weight tree PD will turn out to be some kind of upper bound for network PD, and min weight tree PD will be a lower bound for network PD. Okay, so, but in itself, there are also measures, kind of natural measures of PD on networks. So we can again look or think about the optimization problems. And so let's start with max weight tree PD. So here the problem is now max weight tree PD, where we're trying to determine the maximum value of max weight tree PD over all subsets S of the leaves of cardinality K. And for this particular measure, it turns out that this optimization problem can be solved in polynomial time. So this is one measure where it's solvable in polynomial time. And the idea for that is that we take our network problem, or the problem of determining the max weight tree PD score, and translate that into a network flow problem. And just to give you an idea for what we do, we choose this very simple network where you can probably find the max weight tree PD by just looking at it. But I'm just going to run you through the way we transform that into a network flow problem. So first of all, we're given our network. And so in the network flow, we interpret the root as the source for the flow. And then we introduce a sink, T prime in this case. And so we do that by first introducing some vertex T that gets connected to all the leaves. And then we connect T to the sink, T prime. And then so we have those additional edges below here. And in addition, we need to introduce some more edges. So we introduce additional edges between the root and all tree vertices of the network. So in this case, as I chose this very simple network, there are only two tree vertices. So we only have to think about two additional edges. Okay, so this is the setting. And now in a network flow, we need some costs and capacities. And we do that in the following way. So first, for the cost, every edge that was already present in the network and had some weight, we just multiply by 1. So the cost for this arc will be minus the weight it had. The additional arcs, they all get cost 0. Those two and all the ones we introduced below. And then for the capacity, all the arcs that were already in the network, they get capacity 1. And so do the 3 arcs in this case that we introduced from the leaves to T, they also have capacity 1. And then for this last or bottom edge, as well as for the additional ones between the root and tree vertices, they get capacity K. Okay, so let's look at an example for K equal to 2, for instance. And so then it turns out as we have integral costs here, there exists a minimum cost, maximum flow. And we can show that this problem or this flow gives us a solution to our max network PD problem. And in particular, what you can see here, if you think about this edge, there's capacity K and K equal to 2. So K is still the number we want to find. So this tells us that at most 2 units can route through this edge. This in turn tells us that at most 2 of the edges connecting the leaves to T are used. Because in a flow, what comes into a vertex goes out. So we cannot have we cannot have 3 units incoming, but only 2 going out. So this is, I should have mentioned this before, everything that comes into a vertex, the amount that goes in also comes out. And so we know that K of the leaves are used. And then we can show that all the edges of the network, the original edges that have non-zero flow on them, and I indicated them in red here, they form a connecting subtree of maximum weight. And in particular, we can be sure that the flow induces a tree structure, because for each arc that goes out of a reticulation, we only have capacity 1. And this means that if you now think about this reticulation, vertex at most 1 edge will be used in a flow. If 2 were used, we would have 2 things coming in, but we can only have 1 thing going out. So this tells us that the flow we find will never have 2 reticulation edges going into a reticulation. Okay, so this is skipping some of the technical details, but this is in general the idea how we translate max all path PD into a network flow problem. So this can be done in polynomial time. Okay, so what about the last measure, min weight tree PD, where the problem is now max min weight tree PD, where we're trying to determine the maximum value of the minimum weight tree PD. And it turns out that this problem is again NP hard. And in particular, we could show that even suppose we have a phylogenetic network N on X and we fix a subset S of the leaves, then even computing the min weight tree PD score for this subset of the leaves is NP hard, even if the network is normal. And so this is for a fixed set, and thus we can show that the optimization problem where we try to determine this value over all possible sets as is NP-hard as well. Okay, so this almost leads me to the end. So we have 4 measures of PD now for networks. We analyze their computational complexity. Almost all of them are hard in general, except for max weight tree PD, which can be done in polynomial time. However, there are some open computational questions. As I mentioned, we don't know about the computational complexity for max network PD on level 1 networks. And we also don't know about the same question for maximum weight tree PD. Another interesting question where we had this result for level 1, so for all path PD, an interesting question would be if we can push the level. So for instance, is it still polynomial time for level 2, or is it already hard for level 2? So that could be another interesting computational question. And then there's, of course, maybe a more biological question, maybe which of those measures is biologically sensible or justified, or other measures that would be better, and how can we define them? Okay, with that, I'm happy to answer any questions, but the paper can also is currently submitted and can be found in arXiv.